we're going to learn now how to find integrals that have certain forms in them, okay? So in this case right here, we're learning about how to find integrals that happen to have the square root of a squared minus x squared in them. Now notice that that looks the same as the denominator in an inverse sine function, right? And if I were to do this square root of a squared plus x squared, I see a squared plus x squared in the integral of inverse trig functions. And I also see this square root of x squared minus a squared inside of secant inverse functions. So the point of what we're trying to do here is to come up with a method of changing the form of these so that we're going to be able to integrate them, okay? So I'm just going to give you one example here. Let's say that we wanted to integrate what? Give me a sec so I could find a good one here. Okay, there we go. So let's say we wanted to integrate the square root of 1 minus x squared dx. So this is our main goal today, is how do I deal with any integrals that happen to have those special square root forms in them? Now, these special square root forms show up relatively often because these come from the Pythagorean theorem, from sides of a triangle. And a lot of times those are the relationships that we actually see, so we are expected to, you know, come up with these methods. So this is not going to be an inverse sine function. Could somebody tell me why the answer to this is not inverse sine of x?
It's not a fraction?
Because it's not 1 over that. That's a huge difference. If I was taking the integral of 1 over the square root of 1 minus x squared, then that perfectly fits into the answer for sine inverse of x. The problem is that didn't happen, so it's not inverse sine x. So we've got to have some other way to integrate this function, and it's going to lead back to our triangles, okay? So we call this trigonometric substitution because we're literally going to be substituting trig functions into this, which some of you may not be crazy pleased with if you aren't proficient with trigonometry, but essentially it's because we can't integrate it any other way. And I want to just recap one other thing. What is the significance, or what is the purpose of doing U substitution? Let's start with that. What's the purpose of doing U substitution?
To make it integral easier.
Go ahead, Carlos, first.
To integrate something easy.
Yeah, to change the integral into something that looks easier. That's exactly the point of substitution. Well, the point of trigonometric substitution is exactly the same. The only difference is we're not going to be saying something like u equals something. Instead, we're going to be kind of going through the back door here, and we're going to look at the fact that this integral shows up inside of a special triangle, okay? So let's see where that comes up, okay? If this right here was our angle called theta, okay, then what would my sides have to be in order to get this to show up as one of my sides?
A has to be the hypotenuse, right?
Okay, let's try that. So A would have to be the hypotenuse. So if A was the hypotenuse, okay, how would this show up?
X could be either of them. It depends on which trig function you're going to use.
There you go. Very good. So I could make X right here. And if that's the case, then I would see, well, let's switch it here. I could make x right here. And if I did that, when I wanted to find this missing side, okay, then I would do the Pythagorean theorem and say x squared, I would say x squared plus this side squared is a squared. So notice that x over a, in this case, represents what trig function?
Cosine?
Cosine. So wouldn't that represent that cosine of theta is equal to the adjacent over the hypotenuse? All right, so that would give me cosine of theta is equal to x over a. So notice that this is already starting to show me how I might be able to do a substitution. That if x over a is equal to cosine of theta, then that would mean that a cosine theta is equal to x. And what I've just done here is I've created a substitution that allows me to replace x with a cosine theta. I'm substituting a trigonometric function into x.
If
Turns
we
out, though,
change,
that cosine is not a good choice, even though we actually could do that. Turns out that we're just going to think about it in terms of what we did before. Remember how when we were finding integrals of functions that had these forms, we only used sine inverse, tangent inverse, and secant inverse? Because all we needed to do was throw a negative on there in order to turn them into the other function. So instead, what we're going to do here is we're going to do the same thing. We're only going to be using sine theta, sine theta, tangent theta, or secant theta. And the reason for that is that the derivatives of each of those functions are all positive. So if I do other substitutions, I'd have to focus on making sure my negatives follow along and that I don't screw up my negatives somewhere. So we're just going to force all of the derivatives to be positive as well. And that's why we're going to choose this to be x. And therefore, the missing side is, sure enough, the square root of a squared minus x squared. So now we're going to go through this process of what we just did here. We see this special form. And so it turns out that if I rewrite this, let's look at what ends up happening here. This would come from the triangle sine of theta equals x over a, which means that we have a substitution that x is equal to a sine theta. So that must mean that I'm going to be able to replace this a sine theta into x. And that's what we refer to as trigonometric substitution. You'll see why shortly when we start to do an example as to why this works out. But the whole point of this trig substitution is to cancel out that square root. The square root is what's causing this to be a challenging function. So if that square root wasn't there, then I would be able to integrate it a lot easier. And the way that we're going to be able to get rid of that, as you'll see shortly, is by turning this into a Pythagorean identity so the square root cancels. Okay? But notice that because we're dealing with integrals, that means that we're going to be having dx involved as well. So that would mean that once you have the substitution, the appropriate substitution you're going to use, that means that you need to come up with your dx as well. In this case, dx is a cosine theta d theta. I just integrate as normal. And notice that each of my dx's would then be able to switch with a cosine theta d theta. So anybody have any questions on this right now? When you see a squared minus x squared, okay, that's what's going to end up happening. Okay, so one more time. When you see the square root of a squared minus x squared, the substitution we'll use is a sine theta. Similar to when we saw this, we used sine inverse. Well, now the substitution is a sine theta. Okay, Questions there? All right, well, let's go back to this example then. So this right here looks like what I just saw, the square root of 1 minus x squared. So because it looks like that, then that would mean that this looks like this looks like the form it's supposed to. So I'm going to end up rewriting this. Okay, I'm going to say let's let x equal 1 sine theta. Because notice that in this case right here, a is 1. If it was 9, then I would let x equal 3 sine theta. Okay. All right, well, that would mean that my dx would have to be replaced as well. So dx is equal to cosine theta d theta. And now when we make that substitution, let's look at what happens. We get the square root of, you know what, I would like to change this if you don't mind, because this one is actually too easy. I'd like to just modify this. I would like to make this into a 4. Okay, just so we can see what happens with that a. All right, so we okay with that? So how does that change things?
It would be 2 sine theta.
Yeah, so now I would realize that my x value is 2 sine theta, and that would mean that my dx is 2 cosine theta. Not that big of a difference, but I just want to show you what happens when we end up having an integral like this. All right, so let's go ahead and make our substitution. So we now get 4 minus 2 sine theta squared. And dx is going to be replaced with 2 cosine theta d theta. Now you might realize, man, that substitution just made it look a lot worse. Don't worry, trigonometry is a beautiful thing. So what exactly did making this substitution, or rather how exactly did making this particular substitution help? Anybody see what ended up happening?
You can pull out the 4, and then it becomes 1 minus sine squared theta, and then 1 minus sine squared theta equals to cosine squared theta.
Yeah, and why did that help?
To cancel out with the dx.
To cancel out with the dx. Well, the dx didn't cancel.
Never mind.
Okay. So
Square root and the square
gets
cancel
rid
each
of
other
the-
out.
that's what the deal is. The
subtraction.
square root canceled with the square. So notice that then you ended up getting it down to another trig function that was integrable. So let's go ahead and take a look at the work then. Okay. So if you take a look at the work, you could see that by replacing this form way up here with 2 sine theta, that caused this 2 sine theta to become 4 sine squared theta, which also had a 4 here. So I could cancel out that coefficient by factoring it out, and all that's left here is 1 minus sine squared theta, which is cosine squared theta. And that, if I were to choose any other substitution, the trig function or the square root wouldn't have canceled. I had to pick sine theta in order for that square root to cancel. And not only that, I had to pick a sine theta because when I square 2, I get the same coefficient that I get right here, which allows me to factor that out. So I'm going to leave it at that because now at this point, okay, all we would do is use my power reduction formula and we can solve from there. Okay, so a lot of times it'll turn into a form of a power of a trig function, which we learned how to integrate yesterday. Okay, why don't we try this one? The integral of the square root of 1 plus x squared over x dx. So our goal now is to be able to integrate this, but you might notice that if I let x equal sine theta, like I did in the last one, then I would have 1 plus sine squared theta, and that's not a Pythagorean identity. So notice that my goal here is to try to find some x value that's going to allow me to get a Pythagorean identity so that I could change it to cancel the square root. Okay, let's go back here. So what trig function would I use here in order to fill in my triangle if I need to see an a squared plus x squared?
Tangent.
Yeah, I'd have to use a tangent because I'd have to recognize that either this is a and this is x if I have an angle theta, right? So if that's my angle theta. So if that's the case, then what trig function would I be applying? In order to compare these two sides, what trig function would I use here?
Tangent.
Tangent. Okay, so it would be tangent of a over x. But I want to get x over a because let me just show you why I would want that. If I put the tangent of theta is a over x, then notice by cross multiplying I get x tan theta is equal to a, and then I get x is equal to a over tan theta.
So then cotangent.
So that's why I wouldn't really want to use that. So instead, that would be cotangent.
You would switch the x and a on the sides, right?
Yeah. So that So the point of this here is that I could use a over x, but instead, why don't we use x over a to force that to be tangent? So if that's x and that's a, then use the Pythagorean theorem gives me my missing side, which is the square root of a squared plus x squared. So the whole point of this is that missing side shows up when I use tangent. So if I say tangent of theta equals x over a, then that means that a, or x, is equal to a tan theta. Well, if x is equal to a tan theta, then dx is equal to a secant squared theta d theta. So that means that anytime you see this type of form inside of an integral, then the substitution that you should make, okay, is right here. Replace my a tan theta in for all of your x's. So notice the substitution that's being made. We're not converting x's into u's anymore. We're converting x's into what?
Thetas.
Thetas. Yeah, so we're converting x's into thetas now, and thetas show up as angles, and angles show up in trigonometry. So you can see that that's the purpose of converting into trigonometric functions, because these types of forms show up in trigonometric, well, triangles. Okay. So let's return back to the example, and now I'd like you to do this start to finish. We would need to let x equal 1 tangent of theta, or just tan theta. Okay, and then you'll go from there. Let's go ahead and take a look at the kind of the process that you would have taken here. So notice first of all that the derivative of tangent theta is secant squared theta, right? So the point of this is convert this into a trig function so that 1 plus tan squared theta in the top becomes, by Pythagorean identity, secant squared theta. And the square root of secant squared theta is just secant theta. So all that's left here is secant theta times secant squared theta, which is secant cubed theta, over tan theta. Now the advantage of this is that there's no more square root. The disadvantage is that now I've got some powers of trig functions to deal with. So anybody got some ideas on, or was able to work through maybe part of the process here of how to integrate from this point. Because keep in mind, the whole point of being able to use any sort of substitution is to turn it into an integrable form. Not necessarily make it easier, but turn it into a form that we know how to integrate. So anybody got some thoughts?
Can we separate the secant cube into secant squared and secant?
Yeah, so then it could turn back into something like this up here. And yeah, so we could do that. Which would mean that we just convert it back up here again into secant theta, which is the form I guess it was before I converted it into secant cubed theta. Okay, sure, so you can do that. Okay, other ideas?
We could make it so that it's secant cubed theta, or however you want to phrase the secants, times cotangent theta, and then you could turn that into cosine theta.
So you're thinking use some identities to maybe make this look a little bit better. Okay, yeah, so why don't we try to do that? I don't see right now, I don't see any reason why changing it to secant times secant squared would help, because let's just say that let's say I made u equal to tangent theta. If u is tangent theta, then du is equal to secant squared theta. And it's very possible that we could still do this. I mean, I'm gonna go ahead and try this before we do what Sean just mentioned. Okay. And I'm gonna do some changing here. So let's make u equal tan theta. Then that would mean that du is equal to secant squared theta d theta. So in this case right here, notice that we changed from x's into thetas, and now we're going to see if we can maybe use some u substitution. So this becomes the integral of secant theta over u times du. It's looking a little better, but the problem is I still don't know what secant theta is. So does anybody see any way that I might be able to replace secant theta with u's? All right, there's nothing up here that says what secant theta is, so how could I replace secant theta with u's?
I was gonna say make like secant theta like 1 over cosine theta, but I don't see how that's gonna help.
Okay, that's a good thing. That's a good point too. Make secant theta 1 over cosine theta. Problem is I don't see a cosine theta up here as well. So the only way I'm going to be able to replace secant theta is if there's a way to maybe manipulate tangent theta to have secant theta.
What if we did like?
Go ahead.
Sorry. What if we did like the integral of secant theta and then like times the integral of u to the -1, and then we know the integral of secant theta is like that ln parentheses.
No, we can't do that because this is a product of two functions. And secondly, you can't integrate something that has thetas and u's, because I'm integrating with respect to u, and so I can't start integrating unless everything has a u.
Why don't we turn tangent theta into sines and cosines and then somehow manipulate that to get secant?
That's also a great choice. Again, because we're trying to use some identities to convert this entire secant theta into u's. Well, I know tangent theta is u. I don't know secant theta. So the first thing you should start thinking is, how can I make secants and tangents combine? And the only thing that I can think of is the Pythagorean identity that says that secant squared theta is equal to 1 plus tangent squared theta. Well, that would mean to me that secant squared theta is equal to 1 plus u squared, which would mean that secant theta is equal to what?
The square root of 1 plus u squared.
Great, the square root of 1 plus u squared. So if I replace this with the square root of 1 plus u squared, I get right back to what I started with, and that didn't help me at all. So that was a starting point, and maybe I try to do it, but notice that it didn't really get me to somewhere where it was beneficial, okay? And that's gonna happen quite often, right? You try something and it just doesn't seem to really give you anything that works nicely. So that was a poor choice of u substitution. So let's go to what Sean was saying, okay? Sean, you were saying to do something different. What were you saying?
So what my thought was, if you take that tangent in the denominator and flip it to being a cotangent up top, so you don't have a fraction anymore, you could then use an identity between one of the secants and cotangent to get
so cotangent theta, so I mean, so it would just be manipulating it to try to get some other trig function. So you're thinking, well, I know, why don't we just do this? Why don't we convert this into 1 over cosine cubed theta, and then cotangent theta is cosine theta over sine theta. And so notice that that simplifies into 1 over cosine squared theta sine theta. Again, I am not real sure if this is going to be easier to integrate, because if I let u equal either sine or cosine, then I'm still running into an issue, because notice these are in denominators. So there's no sine theta d theta anywhere to be the derivative of cosine, and there's no cosine theta d theta anywhere to be the derivative of sine. So this was also a good thought. It doesn't seem to work. I can maybe simplify this a little bit better, and I can convert this here. I can convert just 1 over cosine squared theta to be secant squared theta, and then I can convert 1 over sine theta to be cosecant theta. So that's maybe a possibility. So why don't we rewrite this as the integral of secant squared theta times cosecant theta d theta. So it looks maybe a little bit better. I mean, if you take a look at it, this here had 3 secants and a tangent. It was also a fraction, which was kind of a pain. Now down here, you could see that it's got a smaller exponent on secant, and it's got a cosecant. But we're still just running into this situation where we just kind of run in circles. We did u substitution last time, and it just turned it right back into what we started with. We're trying some identities to try to make it look better. What are we kind of learning here? I'm doing this for a purpose.
It's impossible.
No, we're not saying that it's impossible just because we can't do it. So be careful with what our assumptions are here. Just because it doesn't seem like we could do it doesn't mean it's impossible. Okay? What should we be recognizing here?
Integration by parts.
Okay, so that's another option. Before we try that, the point of what I was getting at here was the point of what I'm getting at is that whenever we're faced with a difficult integral, we don't know how to integrate it. So we just try things. The first thing we tried was trig substitution, and we got to the trig substitution, and it turned into powers of trig functions. Then we get down to this powers of trig functions, and we're like, crap, now what? So then we tried u substitution, and it didn't really seem to work for us. So then we said, man, okay, well, maybe we could do some trigonometric identities. And so that's what we did here, did some identities. But we start to exhaust all of our possibilities, and there's only one other option that I see we could use, and as Abby noticed, integration by parts. If I see a product of 2 functions, then the first thing I start to think of is maybe I could use integration by parts here. Okay, so why don't we try that? So now at this point, what might I choose for my u and my dv? Remember
dv
this.
secant squared theta.
Yeah, why would you choose dv to be secant squared theta?
So when you take the integral, it would be tangent.
Yeah, there we go, because it's got a nice, easy integral. Which means we're going to let u be the other part, which is cosecant theta, and therefore du will be the derivative of that. Okay?
Negative cosecant cotangent.
Negative cosecant theta, cotangent theta, d theta. So notice what was cool about this was that if you applied this integration by parts, you got u times v, which was just cosecant theta tan theta, minus the integral of v tan theta du. And what was awesome about that was that the tangent theta times cotangent theta, those are reciprocal functions, so they cancel. So pull that negative out, and all you're left with is the integral of cosecant theta d theta, which we know how to integrate. And again, if you don't know how to integrate, then that's okay. Write a flashcard and memorize it. So the integral of cosecant theta is the negative natural log of the absolute value of cosecant theta plus cotangent theta. But you see the process we used there?
I don't think we can see what you were drawing there, Professor.
I am very sorry, because I was not sharing. My apologies. Resume share. It was totally my bad. So let me kind of go through that one more time. So you can see here that if I applied u times v minus the integral of v du, notice that the tangent theta times cotangent theta are reciprocal functions, so those canceled. So if I factor out this negative, then I'm left with the negative of the negative, which is positive, and now I'm just left with the integral of cosecant theta d theta. So integration by parts allowed me to reduce this integral to something that was integrable, or that I knew how to integrate. So notice that the integral of cosecant theta is the negative natural log of the absolute value of cosecant theta plus cotangent theta. Still kind of a complicated integral overall, but let's just bear in mind what we were doing in the first place. The whole point of this was integrate the square root of 1 plus x squared over x dx, and the only way we were able to do that was by trigonometric substitution and integration by parts. So this had two components that we had to apply. And how did we know to do that? Well, there were two things. When I saw the square root of 1 plus x squared, that automatically indicates trig substitution. Okay? Not automatically. I should say that sometimes when it's in that form, you could just use u substitution directly. So if you recognize that u substitution works, there's no reason to do trig substitution. But we did trig substitution. We got it to a point right here to where we have secant cubed theta tan theta d theta up top. And after a couple of times of simplifying this using identities, we saw that it was a product, so we used integration by parts.
So the integral of cosecant is negative ln absolute value cosecant theta plus cotangent theta?
That's right. Okay. So who'd like to tell me why this is wrong?
Can you simplify more the cosecant theta and tangent theta?
Yeah, so you think of maybe I could start canceling out some things, right? So I could see cosecant theta is 1 over sine theta, and tangent theta is sine theta cosine, or sine theta over cosine theta. So you could maybe see, first of all, that this thing right here, this thing simplifies to secant theta. And if you don't see that, then do it off to the side, but it's 1 over sine times sine over cosine is 1 over cosine, which is secant. So maybe that's one thing you could do. You could simplify it a little bit more just to make it look a little easier. So that's a good choice.
It's
So then,
in terms of theta now instead of in terms of x. Do we need to
very
change
good.
it
Who
back?
said that?
What?
Who said that? I didn't see.
Dylan.
Dylan, thank you, Dylan. Yes, that's absolutely right. The point of this problem was integrate this function way up here. So shouldn't my answer have x's, not thetas? So if I'm trying to find the integral of this function of x with respect to x, I better get a function of x, not theta. And this is where we now need, anybody?
Triangle.
A triangle. So notice that at the end of the problem, we just needed to refer back to, the fact that, here, let me just go ahead and continue to rewrite this. Negative ln of the absolute value of cosecant theta plus cotangent theta. Now, if somebody left it in the form in the red box, that's obviously totally fine as well. It's the same thing. Somebody just noticed that maybe you could simplify that cosecant theta, cotangent theta. But this is where it's important to draw your triangle now. We have to remember that if x was equal to tan theta, that was the original substitution, remember? Then that must mean that there's a corresponding triangle for this. So let's make that theta. And so how can I fill in this triangle?
Wouldn't it be the same triangle we used in the beginning?
It would be from that derivation. But the reason for this is if x is equal to tan theta, or in other words, opposite over adjacent, then doesn't that mean that this would be the opposite and this would be the adjacent and this would be, by the Pythagorean theorem, square root of x squared plus 1? Now let's look at why this is important. Because if I want to find secant of theta, it's hypotenuse over adjacent. I'm screwing up here. So this right here, secant of theta is the hypotenuse over the adjacent side. It's the reciprocal of cosine. And then cosecant of theta is the reciprocal of sine. So that's going to be the hypotenuse over the opposite side. And I know the cotangent is going to be the adjacent side over the opposite side. So you can see that if I'm going to convert this back into x's again, then I need to know that each of these ratios represents the ratio of two sides of a triangle. So finishing this up gives me...
Can't you just put tan inverse of x every time you see a theta?
Yeah, that would be extremely ugly. I mean, you could say secant of tan inverse of x minus ln of cosecant of tan inverse of x plus cotangent of tan inverse of x. That is ugly. Not only does it involve trig functions, it involves inverse trig functions, and it involves trig functions of inverse trig functions that are hidden inside of logarithms. So even though that is technically correct, it's not typically the way that you do things with trig substitution, because there's always a corresponding triangle. So instead, you draw the triangle and you now fill in the blanks. Okay, so let's look at the hypotenuse over adjacent. Hypotenuse over adjacent is just the square root of x squared plus 1. Minus the natural log of the absolute value of hypotenuse over opposite. Well, that's just going to be the square root of x squared plus 1 over x plus the cotangent theta, which is adjacent over opposite, which will be 1 over x plus c. And that's our final answer. Okay, so our final answer should be an algebraic function. It doesn't involve any trigonometric or inverse trigonometric functions anymore. And there's our answer. So that was kind of an interesting one, pretty crazy one, right? But the idea was that if we go back to the beginning, I'll leave it on this slide or part of the slide for a minute. But if we go back to the original, I want you to just remember what the whole purpose of this was. This was to find the integral of the square root of x squared plus 1 over x. Right? Dx. So the whole purpose of this was to actually integrate that function to get some other function. We just used trigonometric functions in order to turn it into a form that was integrable. But then when we did that, we got way back to here. We got to this step right here. That's what trig substitution did. A lot of times trig substitution will turn it into a much easier function. This one right here turned it into a function where I wasn't quite clear what to do. So we did a couple of identities to make that trig function look a little bit better, which ended up taking me down to this one. Right? So when we got to here, now we were able to use parts, integration by parts.
Would you consider this to be like an easy problem? Like on the exam, there would be something more complicated?
No, this is not an easy problem.
All right, thank God.
Normally in class, I don't do the easy problems. I mean, I want to show you some of the trickier things that occur so that when you are faced with something a bit easier, then you can handle it. Now, I wouldn't say that all of these things separately, all of these components of this problem separately couldn't be components of an exam, but I would never put a problem on an exam that was like this. I'll be perfectly honest. Because this requires you to not only, not that I don't expect that many of you can do this or should be able to do this eventually, but it requires us to first of all know what trig substitution to use. It requires us to apply the trigonometric identities correctly to simplify. But then it requires me to have a little forethought about using some more trigonometric identities to simplify what we see here into some form that we can integrate. And then to recognize that, sure enough, to integrate a product, we have to do integration by parts. And then you get to the final answer, but then we still have to draw the triangle. There's just so many different components of this problem. I would never put this on an exam, but the idea of this is to show the process of trig substitution and also how turning it into a form with trigonometric functions can then be integrated. Okay.
So then I have a question about like the first example that we went over, which was 4 minus 2
square root of 4 minus x squared.
Would we be going back to the triangle and going back to make our final answer in terms of x's as well?
Yes. So that's a great question. I should have, going back to this one here. Okay. You would then integrate but notice that in integrating, you would have a function with thetas, so you'd have to use the corresponding triangle. So I'll go ahead and help you to draw the triangle so you know what to use. Okay, but the triangle would just be based off of, okay, the fact that x was equal to 2 sine theta. So we said that x was 2 sine theta, which means x over 2 is sine theta. So now we can fill in the triangle that in relation to this angle, the opposite side is x, the hypotenuse is 2, and therefore this side is the square root of 4 minus x squared. Okay, so notice that once you get to the point of any integral involving trigonometry, if you start with the function of x, you better end with the function of x. So that's why the triangle comes in handy, so that you can actually replace whatever functions show up inside. Okay. we good there? I'm looking at this and kind of realizing that this could have a kind of an interesting situation pop up. So I feel like maybe I should integrate this function. So let's integrate this real quick. So this becomes 4 times the integral of 1/2 minus 1/2 cosine 2 theta.
Shouldn't it be a plus?
Plus, thank you. So what we're really doing here is we're taking the integral of 2 d theta, because that's 4 times 1/2, plus, and then we've got 4 times 1/2 again, so we've got the integral of 2 cosine of 2 theta d theta. Okay, so what does this become then? So we can see that the integral of 2 d theta is 2 theta plus. Over here, notice that we've got cosine of 2 theta, and the derivative of 2 theta is 2. So we see that we're already in the form that we need to. The integral of cosine 2 theta times 2 is just sine 2 theta plus c. So I'm going to leave it at that for a second. I'm kind of glad now that I did this that I didn't just stop back at the cosine squared theta because there were a couple of subtle little weird things that occurred here when you integrated. So first of all, when we had 2 theta plus sine 2 theta, there's no way that I could figure out what sine 2 theta is if I'm given a triangle with the angle theta. So that's why the first thing I needed to do was convert sine 2 theta by using the double angle formula to be single angles. So we replaced sine 2 theta with 2 sine theta.
I don't think you're sharing the screen.
Thank you again. I'm sorry, I keep pausing it when you go into your breakout rooms. So when you see sine 2 theta, there's no way for me to figure out trigonometric ratios if I'm given a triangle with theta. So instead, I have to convert sine 2 theta into the double angle identity. Because with this double angle identity, I now have single thetas that I can start replacing. There's another weird thing over here. 2 theta doesn't have a trig function. So the only way to solve for theta to replace that is to go back down over here and realize that sine inverse of x over 2 is what the value of theta is. So the final result here just simply gives me 2 sine inverse of x over 2 for the 2 theta part. Notice the 2 sine theta together. Notice 2 sine theta. That's just x. 2 sine theta was x, so I just replaced that with x. And then I looked at cosine of theta and realized that cosine is adjacent over hypotenuse. So that's where the adjacent over the hypotenuse came from. Okay. And that would be our final result for this problem.
I'm kind of having a little brain fart. Like, how did you get from sine 2 theta to 2 sine theta cosine theta?
That's the double angle formula for sine.
Okay.
Sine 2 theta is 2 sine theta cosine theta. You can see there's a lot more trigonometry involved in Calc 2, especially in this first part, involving the powers of trig functions and the trig substitution and so on. The trigonometric identities come up quite often, so just got to try to continue to get a handle on those. All right, this one here I could see definitely as fair game for an exam, to be honest. This right here is a great problem. It's straightforward enough to where it's a simple trig substitution. It requires us to do the power reducing formula right down here for 4 cosine squared theta. And then it requires us to think a little bit for our triangle, okay? All right. Well, I'm not going to do another example, but what I am going to do is just do this last derivation for what if you see x squared root of x squared minus a squared. So this one right here would show up if I were to have an x value as my hypotenuse, and any one of these two sides, either this being a or this being a, okay, not both at the same time. So we want to force everything to be positive. So that's why we're going to say secant theta. So secant theta, remember, is hypotenuse over adjacent. So we're going to call this side A. And if we do the Pythagorean theorem, we end up finding out that that missing side will be a squared plus this side squared, a squared plus the height squared equals x squared. So that means that the height is going to be the square root of x squared minus a squared. So that special radical showed up in the formula, or in the triangle for secant theta. Okay, so let's go back and let's just recognize that we're making secant theta equal x over a, because that's equal to hypotenuse over opposite. Okay. All right. Well, if that's the case, then we can see that by multiplying both sides by a, we now get a new substitution that x could be equal to a secant theta. All right. And just like we did up here, that means that if x was equal to a sine theta, we plugged that in for x. If we let x equal a tangent theta, we plugged that into x. So if we see that x is equal to a secant theta, the whole point of that is that we can plug that into x. But if we're going to do that, dx's show up as well in an integral, so I've got to rewrite this as a secant theta tan theta d theta. And after that substitution, hopefully it gets to an integral that's a lot more manageable. Okay, so a few of the problems that you're going to run across in 3.3. Most of the time it's great when we could make these substitutions and you look at the integral and you're like, yes, that is a beautiful, simple integral. I did one earlier, obviously, where you changed it and we got secant cubed over tangent, which didn't look like it was much prettier. So we had to get a little creative by trying a couple of other methods, okay? But just understand that what we're looking for are these three special forms: square root of x squared, or a squared minus x squared, square root of a squared plus x squared, or the square root of x squared minus a squared.